Researchers at Duke University have implemented a new method to observe a quantum effect in the way light-absorbing molecules interact with incoming photons. Known as a conical intersection, the effect puts limitations on the paths molecules can take to change between different configurations. The method makes use of a quantum simulator developed from research in quantum computing and addresses a long-standing, fundamental question in chemistry critical to processes such as photosynthesis, vision, and photocatalysis. It is also an example of how advances in quantum computing are being used to investigate fundamental science. The research was supported in part by 2 grants from the U.S. National Science Foundation. The results appear in Nature Chemistry. As soon as quantum chemists ran into these conical intersection phenomena, the mathematical theory said that there were certain molecular arrangements that could not be reached from one to the other, said Duke engineer Kenneth Brown. That constraint, called a geometric phase, isn't impossible to measure, but nobody has been able to do it. Using a quantum simulator gave us a way to see it in its natural quantum existence. Measuring the quantum effect has always been challenging because it is both short-lived and small on the scale of atoms. Any disruption to the system will prevent its measurement. While many smaller pieces of the larger conical intersection phenomenon have been studied and measured, the geometric phase has always eluded researchers. The researchers used a 5-ion quantum computer that uses lasers to manipulate charged atoms in a vacuum, providing a high level of control. Because the quantum dynamics of the trapped ions are about 1 billion times slower than those of a molecule, the scientists were able to make direct measurements of the geometric phase in action. The experiment, Brown says, is an example of how even today's rudimentary quantum computers can model and reveal the inner workings of complex quantum systems. The beauty of trapped ions is that they get rid of the complicated environment and make the system clean enough to make these measurements, said Brown.